Hey everyone, this is T.A. Yusuf, and today we're going to be doing a video on JK flip-flops. Um, and JK flip-flops are a very useful tool. They can be used in shift registers, they can be used in data counters, they can store memory. They're very useful to us. In this video, I'm going to be mostly talking about how we can use the truth table for a JK flip-flop. We will also talk about some key highlights for the concepts or the theory of a JK flip-flop and the important things we need to remember when we're going to be going to do a problem on them. And then we're also at the end going to do one example problem. So that's what's in store for y'all for this video. And we can jump right into it. Before in this course, we've been working with combinational circuits. That's our AND gates, our OR gates, our XOR gates, all of those where we're working with signals. And we can draw our gates, and we have these digital signals leading up to an output, and we can say, okay, when X is 1 or when Y is 1, we have output is this. And all those are instant. Comparatively, when we're working in sequential circuits, they work slightly different. Whenever I have my combinational circuit, it is always going to be, my output's always going to be based on my current inputs. So my output is based on my current inputs. For a sequential circuit, it's based on the past sequence of input values or the state that it was in, and also dependent on the present. So this will be very important when we go to our truth table, because our output is going to be based on what we had the cycle behind and what we have in the current cycle. So this is going to be very important to us. This second idea is in a clocked flip-flop, the output only changes when there's an edge on the clock input. When we scroll down below, we'll see what those clock signals look like, but you really have a T waveform. It goes up, down, and depending on what edge active clock you have, whether it's a rising edge or a falling edge active, that determines where your change will happen. That determines when your output can actually change to reflect that change in the clock signal. And that's reiterated in this third bullet point. In an edge-triggered device, the output doesn't change unless there's a specific edge of an input signal. In this video, we're going to be working with the rising edge of the clock. So all of them are going to be on these rising edges. If we look at our clock signal right here, right when it goes 0 to 1, if this is 0, this is 1. Right when it goes up, that's one of our rising edges. When it goes down right here, that's an example of a falling edge. So we're not going to have a change there when we reflect it on our timing signal for our flip-flop. Only the rising edges. So this is another one. We have another one right here, another one right here. So hopefully that helps. That was just a brief overview of the important concepts for our JK flip-flop. And on the left here, I actually have the inside of our JK flip-flop. And we have an SR flip-flop. And we see we have some looping going on. We have some feedback with our Q and the complement of Q. And we can actually trace through each condition if we're looking at J and K as our two inputs and generate a truth table from there. And we can say, okay, what happens when J is 0 and K is 0? What happens when J is 1 and K is 1? We can do that through this combinational circuit. We already have that over here on the right side. The reason why I'm showing this circuit is just so we're not saying, oh, how did this come out of nowhere? This truth table is based off of this circuit. This circuit we should be somewhat comfortable with. These are things we have worked with before. We have two NOT AND gates right here. So two NAND gates. And then actually we have two more NAND gates. So it might be sometimes a little bit difficult to follow, but we should be comfortable with all those components in that example. So this takes us to our truth table. Okay? We've talked about the concepts. We've talked about where this truth table is derived from. Let's talk about what's different in this truth table compared to our regular truth tables in combinational circuits. If I switch colors real quick. Okay, one of our first differences here now we're going to be working with our clock signal, okay? And this is just saying that we're going to have a rising edge clock for this entire component, for this entire truth table. So this is important to us, but it's not changing. So that's okay. This is fine. And as always, we have our inputs on the side here. If I'm checking to see if I have every case, if I have 2 inputs, I should have 4 cases. 0, 0, 0, 1, 1, 0, 1, 1. I have all 4 of my cases here. Okay. And now I have the output. Usually for our truth tables, the outputs are always 0, 1, 0, 1, 0, 1. Here, it's a little bit different, but that's okay. We don't have to be too worried about it. It'll make more sense when we do the simulation waveforms and we can see that there's no change happening or there's a clear happening. But a simple walkthrough of them, when it's 0, 0 is our inputs, our Q is going to be no change. So whatever signal it was previously, it's going to stay the same. If we have 0, 1 as our inputs, we're going to have a clear signal being passed, and that means that whatever our Q was goes to 0. So if it was a 1, it goes to a 0, or if it was a 0, it stays at 0. Set is the opposite of that case, and it has the inputs of 1 and 0 for J and K. And so there, a 0 would become a 1, or the 1 would stay the 1, okay? And this last example, where J and K are both 1 for your inputs, you have this Q's complement. So whatever Q was before, it's going to flip, it's going to toggle. So if I had a 0, it becomes a 1. If I had a 1, it becomes a 0. I'm going to walk through each example independently, and we're going to draw them out just so that we can see it happen, okay? So this is this first case where we had no change for our Q. We had no change, okay? And I have 2 waveforms here. One is going to say, okay, let's assume Q starts at 1, or we can start Q starts at 0 for this one, and Q starts for 1 here. And we're going to see how the flip-flop works in respect to our clock signal, okay? So basically, our J and Ks are going to be constant. It's 0 and 0, and we're going to see how this changes in terms of the clock signal, okay? So very first, we're at the beginning, okay? 0, we said Q is going to be 0 for this first waveform. And we're saying when we have these 2 inputs, J and K of 0, we're going to have no change. So this is our first rising edge of our clock. So here is where we'd have our new line. And based off of our Q, we're going to have no change. Okay? And then I'd go to my second rising edge and I'd look here. Okay, this is where my second case would happen. And I'd look at my inputs again. In this case, my inputs are staying constant, so I know there's going to be no change throughout this entire thing. Okay? And that's because my J and K are staying constant. This waveform is not too interesting to me, but it's showing me how the outputs work and how I should be thinking about how the clock should work. Okay? Alternatively, if Q started off as a 1, so we have 1 right up here, and this is my first rising edge, it's the same thing. I have no change if these are my inputs, so I'm just going to continue this line all the way to the end. Okay, so that was our easiest one. That one should be pretty simple. I'm going to go ahead and move on to the next scenario, and that's when J is 0 and K is equal to 1. And this mode of the flip-flop is called clear. And a reminder, this is setting our Q to 0, okay? Clear. So you can think of it clearing it or erasing it. We're setting it to 0, okay? And just like what we did above, this first waveform is going to be Q equals 0 initially, and the second waveform is Q equals 1 initially, just so that we can see what happens in both cases, okay? So if I'm saying Q is 0 initially, we go here. This is my first rising edge. This is where I can see my first change or expect to see my first change. It says, okay, I have J as a 0 and K as a 1 for my inputs. I should be clearing my signal to 0. So it's already 0, so it stays 0. In this case, because my inputs once again are constant, I'm not going to be changing at all. So same idea as above. Okay. So now, in this case, if I said Q was initially a 1, I'm going to this first rising edge, and now based off of my inputs, I'm saying I should set it to 0. So now I will see a change, okay? This 1 goes to 0, okay? And that will stay there until the next rising edge. So I'm going to draw this line all the way to the next rising edge, okay? And since our inputs are constant, it's going to stay the same for the rest of the circuit. But with this fourth example, we have now seen what it would look like in a real waveform. We've seen it change at a rising edge due to the conditions of the flip-flop. So this is what we're building to. But so now we've looked at how it behaves with the original of Q equals 0, original of Q equals 1, and we can know what to expect when we have our inputs changing, okay? Our next example is going to be the set example, and this is where J is 1 and K equals 0, okay? Make sure I have the, okay. And this is setting it, this is when we set Q equal to 1, okay? Just like before, we have two waveforms. Let's say Q equals 0 originally up here, and Q equals 1 originally up here. I'm going to draw this 0 to my first rising edge. At my first rising edge, my flip-flop is in the set mode. So I'm going to set this equal to a 1. This will be in a 1 until the next rising edge. Okay, that I'm at my next rising edge. Once again, inputs are constant, so it's going to stay at 1 for the rest of the time. But here we also see, okay, we have an instance of where we're working with a different kind of circuit now. In this sequential circuit, I had to wait for my clock change to change signals for my Q, okay? Alternatively, so now I'm going to my second example where Q starts as a 1, okay? I go to my first rising edge, and here we're in the set mode. It's already a 1, it's going to stay 1 the entire time, okay? Now we're going to our fourth example, and this is that toggle scenario where Q is going to become Q's complement. We're really saying, okay, if we're at a 0, becomes a 1. If we're at a 1, becomes a 0. This is our fourth mode, and we will be able to see a lot here and be able to talk about the rising edges a lot in this format, okay? So let's just say, to start off, my Q is equal to 0, okay? Q equals 0 at my first rising edge. Perfect, okay? I'm in my toggle mode. So if I'm at 0, now at this rising edge, I'm going to go up and I'm going to become a 1. I'm going to stay at 1 until my next rising edge, okay? And I'm a 1 all the way until the second rising edge, okay? In this case, the toggle, we're saying, okay, it's based off the previous state. Previous state was a 1, so now we're toggling it to 0 at the second rising edge. So this case will change. This case will change as compared to the other examples. So now we're back at a 0 at the second rising edge, and this will continue until the third rising edge. And this will keep on repeating and repeating if we're staying in the toggle mode. If these inputs are remaining constant and staying in the toggle mode, we will see a similar waveform up top, but it'll be for every rising edge. So here, I'll go back up until here, go back down, here, go back up, here, go back down, and lastly here. And that's our signal for toggle. Okay, hopefully those first four examples made sense, and we should be able to move on to a more real example. Okay, below here I have the J-K flip-flop timing example. Here we're given a J, K, and clock signal, and then they're asking us, can you draw the Q signal in the spot above, okay? Different from the last example, we can see our J and K inputs are changing. Our clock signal is that same period, it's the same T waveform, so this is what we just use this. So we are familiar with this, but now our J's and the K's are flipping signals, they're flipping values. We got to be careful, and we got to make sure we're looking at the right thing and looking at the right mode. So let's pay attention to the rising edges, and the mode of the flip-flop. Okay? So I'm going to do two different ways of doing this example, and you can choose whatever way works best for you. I'm going to choose the second way as my favorite just because it helps me stay organized. This first way is going individually. Let's look at what we see and what we have for our signal. Okay? Let's start by finding the first rising edge. That's where we know we'll have our first change. Okay? First rising edge is going to be right here. So we know this is where we're going to have our first change, and our Q is starting at 0. Okay? So our Q is starting at 0 here. Just draw it right here. This is given. Q is starting at 0. At this rising edge, I'm going to change states. I'm going to change modes. What mode am I changing to? Let me look at my two inputs. So my J is a 1, and my K is a 0 right now, okay? So I have 1 and 0. And based off of my truth table, when J is a 1 and K is 0, I'm going to be in my set mode. Okay? So from here, I'd go to a 1, and then I'm going all the way to my second rising edge. And so this was set, and this was equal to 1. That's one of the ways of doing it. So I looked at my diagram, I'm drawing on my diagram, and I'm looking at the inputs for that first rising edge, and then I'm marking and indicating it so. Another method of this that we can do is we can write down all of our inputs at once, and then write down all of our Q examples, and then we can actually draw all at once and help us stay a little bit more organized. Okay? So here I've already drawn first, second, third, fourth, fifth. This is all talking about the rising edges in our clock signal. Okay? And I also have J, K, and Q. So I'm going to go ahead and start by just looking at my inputs and writing down what signal that waveform is. So for the first rising edge, my J is a 1. Second, it's still a 1. So now I'm looking here. And if I'm looking at my third rising edge, my J is still a 1. Okay. For my fourth, it's a 0. Fifth, 0. 6, 1. Seventh is 0. This helps me remember where my change is going to occur when I go to get my Q signals. Because if I'm looking at this circle right here, in between or right after the rising edge, my input actually changes. But remember, when we're working with our flip-flops, the change has to occur on the rising edge or on the edge of that flip-flop. So this change won't be important until I get to this fourth rising edge here. So it's important to stay consistent and pay attention to those details. Okay? I'm going to do the same process for the K signal. I have 0, 0, I have 0, 1, 1, 1, and then at my fifth, I have 0, 6, 0, and seventh is going to be 0. Okay. Now I'm going to look at my Q signals, and I'm going based off that truth table that we had earlier. I already said from doing that first example, this is going to be set. And then if I have 1s for both my inputs, it's going to be toggle. Next case is toggle again. I will then have clear. 0, 0 is no change. 1, 0 is going to be set. And then I have no change again. Okay. So now I can draw my waveform all the way throughout. And I want to make sure whenever I do one of these changes, it's based off of that rising edge. So first rising edge, set, we already did this one. That's a check mark. So now I'm at my second rising edge and I know that I'm going to toggle, okay? So I'm at a 1, so what does that mean if I need a toggle? I need the complement of the 1, which is 0. So from here until that next rising edge, which is indicated by these dotted marks for us, which is great, dotted lines, okay, I toggled. So that's my second step. So I said toggle, okay. Third rising edge, I'm going to toggle again. So now I did toggle again. My next step is clear. Remember, clearing, we're setting to 0. We're going to 0. So now I'm going to be at clear or 0 until my next rising edge. And then I have no change. Okay, so I'm at 0. I'm going to stay at 0 until the next rising edge. And then I'm at set. Remember, set means we're going to a 1 until my next rising edge. And finally, no change. So, and if I went back, this was no change. In C, this was set. This was no change. Let me double check everything. I had 1, 2, 3, 4, 5, 6, 7. 7 modes. I had 7 rising edges. That should make sense. And I marked and checked all of my inputs. So hopefully that video helped just getting a general understanding of the JK flip-flops, and thank you for watching.